All right, in this lesson, we are talking all about the absolute value parent function, and then we will be doing transformations. And so starting with the parent function, absolute value measures the distance from zero. So when you see bars around a number, it's measuring the distance from zero on the number line. So if I were to take the absolute value of -3, that is a distance of 3 from 0. -2 is a distance of 2. -1 is a distance of 1. 0 is a distance of 0. 1 is a distance of 1. 2 is a distance of 2. 3 is a distance of 3. And so you can also view these bars as basically just taking the positive value of whatever is inside those bars. So you see -3 equals 3. The absolute value of -2 equals 2. And then also the absolute value of these positive numbers equal the same thing. And so when we graph these points, we see -3 has an output of 3, but so does +3. -2 has an output of 2, and so does +2. -1 has an output of 1, but so does +1. And of course, 0 has an output of 0. And so we're seeing a line of symmetry right down the middle of our graph. Our graph is a mirror image on each side of this, what we call axis of symmetry. And that may be familiar from Algebra 1 when we talked about quadratic functions. So the symmetry is an axis of symmetry. And the equation of this line is x equals 0. This would be the x equals 2 line. This would be the x equals 4 line. This would be the x equals -2 line. And so the y-axis is the x equals 0 line. Vertical lines have an x equals equation because they cross the x-axis. And so it's important that you have that x equals when you talk about the axis of symmetry. Otherwise, I don't know that you're talking about a vertical line. And then this point right in the middle is called the vertex. And for the parent function, the vertex is at 0, 0. After we do some transformations, we'll see that the axis of symmetry and the vertex move. The domain of this function is all real numbers, or -infinity to +infinity, because it goes forever to the right and forever to the left. +infinity, -infinity. And then our range, we have a minimum at the vertex, and then the entire function is above that line. And so the minimum value is 0. We have a bracket because we do equal that minimum value. And then it goes to infinity. And so we call this an absolute minimum. We'll be talking about relative in min in another lesson, but this is an absolute minimum. The function never goes below this point, and so it doesn't have a maximum. It keeps going up forever. It has an absolute minimum at 0. We always talk about the y value for max and min output values. Okay, and so this is all the parent function. It's called the parent function because all other absolute value functions are just transformations of this function. So we can move it left, right, up, down. We can reflect it, stretch it, compress it. And so here's our different transformation rules that you may remember from Algebra 1. We're going to summarize it here in a summary chart. If you see a plus or minus number outside the function, so outside the parentheses, and then for the absolute value function, you're going to see it outside the bars. Outside the parentheses means outside the bars, outside the function. This is going to move you vertically. It's going to move you up 3. If it's +3, it's going to move you down 3. If it's subtracting 3, which makes sense. You're adding and subtracting a value to the output. If you add and subtract a value to the input inside the function, it's going to be inside the bars. You're changing the input. And because you're changing the input, everything's opposite of what you would expect, because you kind of have to undo what you're doing to the input, if that makes sense. And so a +3 actually moves you left 3. Even though you would think plus would move you forward to the right, it actually moves you backwards to the left. And then a -3 moves you right 3. Okay, and a negative outside, again, is going to be a vertical change. But if you put the negative inside the bars, it's going to be a horizontal change. So a negative outside the function would be outside the bars. A negative inside the function would be inside the bars. If it's outside, it's going to reflect you vertically. So it's going to reflect across the x-axis. Across the x-axis, meaning it is going from right side up to down. It's reflecting vertically. Whereas if you put a negative inside the bars, we talked about how those bars, after you put the bars on a number, you're taking the positive anyway. And so this negative really doesn't have an effect, but it's actually reflecting across the y-axis. And you're not going to notice a change because the y-axis is the axis of symmetry. So if I take this function and reflect it over the y-axis, it's going to look exactly the same. And so it's important to know that if you have a negative inside the bars, you're not going to see a change. No visible change. Also, if you want to abbreviate these, RX is the abbreviation for reflect across the x-axis, and RY is a abbreviation for reflection across the y-axis. Okay, and so far we've talked about translations, left, right, up, and down. And you do that by adding and subtracting values to the output or the input. The next two that we talked about were reflections. And you do that by adding a negative in front, either in front of the output or in front of the input. The last section we're going to talk about are stretches and compressions, which are called dilations, if you remember that from geometry, but we're very specific in algebra. So dilations, if you have a scale factor outside the function, it's going to be outside the bars. If your value is greater than 1, we call it a vertical stretch. And whatever this number is, that's your scale factor. So by a scale factor of 3, sometimes we just say vertical stretch by 3. And then if you want to abbreviate that even further, you can say VS3. That's what I do. And then if you have a scale factor that's smaller than 1, you're going to say vertical compression. Some say shrink. The technical term is compression. And the fact that you're using compression is just because the scale factor is smaller than 1. It's going to cause it to shrink. It's compress. Okay, and so you can abbreviate that VC 1/3. Okay, if you move that scale factor inside, just like the case of adding and subtracting, it's going to do the opposite of what you would expect because it's happening to the input. And so when it's inside the bars, it's affecting your input. And so everything you think would happen, it's the total opposite. And so this scale factor of 3 is actually going to be called a horizontal because it's inside. And instead of saying stretch by 3, which is what you would think, we're going to call it a compression by 1/3. Anytime you change the input, it's kind of like the opposite because you have to account for the fact that you're changing your input before applying the function. And then if we have a 1/3, that's going to be the horizontal stretch by 3. And so if you want to abbreviate these, HC 1/3, HS 3. Okay, so some ways you can help keep these straight is noticing that when I used blue, they were vertical changes, and everything that was vertical was happening outside the parentheses and outside the bars. Okay, and then anything that was happening horizontally, I did in green, and it's because it was happening inside. It was happening to X. And so X-axis is your horizontal axis. So when you see things happening to X, it's happening in the horizontal direction. And then likewise with vertical. If it's happening outside, it's happening to the output. It's happening in the Y direction. Okay, and then the other way to kind of chunk this information is that your translations are when you add and subtract a value, whether inside or outside. Reflections are the negatives, that's how you flip something. And dilations is when you're scaling something. You have a multiplier out front. Okay, and so when we're talking specifically about absolute value, we want to know how these transformations affect our graph. And so we're going to look at different aspects. And so which transformations affect the domain? The answer to that is none. No matter what you do to the absolute value function, you can stretch it, you can reflect it. It's a V shape. It's forever going to the left, forever going to the right. So nothing changes the domain. It's all real numbers all the time. All real numbers all the time. Okay, and then for the range, several things are going to affect the range, mainly reflections across X-axis. Because if you reflect across the X-axis, your minimum is now a maximum. And so instead of, let's say this was a Y value of 5, your range would now be negative infinity to 5. 5 would be the maximum. The other transformations that affect your range are where you put that maximum. So shifting this value up and down will also affect your range. So reflection across the X-axis and then up and down. Shifting it up and down. Next question is, which transformations affect the axis of symmetry? Well, the axis of symmetry is a vertical line, and so the only transformations that affect that is shifts left and right. If you move it up and down, you're not going to see any change. You can move a vertical line up and down all day long, you're not going to see a change. Okay, and then for vertex, that's any translation. So left, right, up, down, you can move that point just by translating. Left, right, up, down. And then lastly, we want to talk about how thin or narrow the absolute value function is versus how wide. And so in that case, we talk about the slope of each arm. Sometimes we call them a branch. So this is a line and this is a line, and they're going to have a slope, a positive and negative slope. And so the only transformations that affect that are your vertical stretch, vertical compression, horizontal stretch, horizontal compression. So basically anytime you have a scale factor, that's going to determine your slope. And we'll use that to graph each one. Okay, and so now that we know our transformations, we are going to go into graphing our new absolute value functions using the transformations. All right, so here's the steps for graphing absolute value functions. First, as you read the transformations, remember A and B are your scale factors. And then C and D are your translations. Okay, and so you first want to determine where the vertex is. And so if you're moving right C up D, your vertex is now CD. Okay, next you want to determine the direction of opening. And that's really only affected by this A value. If it's positive, that means you don't have an RX, a reflection across the x-axis. And then if it's negative, that means you have an RX. That means it's opening down. And so it's opening up if A is positive, opening down if it's negative. And then next, you're going to graph each arm on each side of the vertex using the slope of whatever A times B is. You take those scale factors, and that's going to act as your slope. Okay, so starting with number 1, let's list the transformations. We have a vertical stretch by 2. We have a right 3. And then an up 1. Okay, and so that means the vertex right 3 up 1 is going to be at 3, 1. Move it right 3 up 1 units. It starts at 0, 0, and it moves right 3 up 1. And then the axis of symmetry, remember, is the vertical line that goes right through the vertex. And so once you have the x coordinate of your vertex, you have the equation for the axis of symmetry. It's going to be the same x value. X equals 3 because it's crossing the x-axis at 3. Domain, we talked about all real numbers all the time, so negative infinity to positive infinity. And then our range, because this absolute value does not have a negative here, it's going to be opening up. And so just kind of sketching to the side, this vertex is at 3, 1. The entire function is above the 1. And so we are going from 1 to infinity. All right, and so now to get an accurate graph, we just need the slope of each arm going to on each side. And so our slope here is always going to be your scale factor. And so our scale factor here is 2, and so that's your slope. And so we're going to go up 2 over 1, up 2 over 1. Remember, slope is rise over run, so 2 is a whole number, and so write it over 1, rise, run. Rise 2, run to the right 1, rise 2, run to the 1. And then you're going to do that same thing on the other side, doing the negative slope, because it makes that V shape. Okay, and so here's our new absolute value function. He's a little bit narrower because of the vertical stretch. When you think of stretching a rubber band, the more you stretch it vertically, the narrower it looks. Okay, next we do have a reflection across the x-axis, so I'm already picturing it opening down. And I know my range is going to go negative infinity to whatever that maximum y value is. Our scale factor is now inside. And so this is a horizontal, and we would want to say stretch by 4, but it's compression by 1/4. Okay, and then lastly, we have a -2 outside the bar, so that's going to move us down 2. Okay, and so our vertex just moves down 2. It doesn't move left or right, so it's still on the y-axis. It's just down 2. From 0, 0 down 2 puts us at 0, -2. And then remember, we can steal the x coordinate to be our axis of symmetry. Domain, all real numbers. all the time. Okay, so now we need the slope of each branch. And so don't look at your scale factor here, look at your scale factor here. And so I don't like that I labeled this 2 as the slope. Label this 2 as the slope, because 1/4 is not your slope. 4 is your slope. The scale factor isn't necessarily your slope if it's inside. Okay, and so our slope is 4, and we're opening down. So that means 4/1, that's our rise, that's our run, but we're gonna go down 4 since it's opening down. 1, 2, 3, 4, run 1. Down 4, run 1 on each side. Down 4, back 1, down 4, back 1. Okay, and so this slope of 4 makes it narrower, which makes sense because we said it was a horizontal compression. That means it's going to be narrower. So when you horizontally compress, it looks narrower, which that means we had a steep slope, a steeper slope. And same with a vertical stretch. Anytime you vertically stretch something like a rubber band, it's going to look narrower. And so both cause a narrower V shape. Okay, next up, we've got a lot going on here. We've got multiple scale factors. This 3 is a vertical stretch by 3. And then this negative alone is a reflection across the y-axis, which doesn't result in any change to our graph. So we can ignore that. And then this 2, it's inside the bars, so we're calling it a horizontal compression by 1/2. And then we have a minus happening to x. That's going to be our right 1. And then lastly, +4 is going to move us up 4. And so the only ones that affect our vertex is the right 1 up 4. Vertex is right 1 up 4, which means my axis of symmetry is x equals 1. Right 1 up 4. There's the vertex. Because there's no negative outside, I know this is still opening up. Okay, domain is all real numbers all the time. And then our range, because it's opening up, it is going from this vertex at 4 to infinity. Okay, and so to color code some of these things, this 4, the y value of your vertex always shows up in your range. The x value of the vertex always shows up in your axis of symmetry. Okay, so now to graph the arms of our absolute value function, we take the 2 scale factors here, 3 and 2, the a and the b, and we multiply them together. So our slope is going to be 3 times 2, which is 6. That's going to be very, very narrow because we are not only vertically stretching to make it taller, we're also horizontally compressing it to make it even narrower. So narrower and narrower. And so we're getting narrower to a slope of 6. And so we would have to go up 6 units, which puts us at 10, right 1 on each side. Okay, and this last one is the hardest one because it's not in the proper form. Notice how I had parentheses here separating the scale factor from x. If you don't have that situation and you have a scale factor on x, you need to factor out the 4 to create that situation. You don't want to see what's happening to 4x, you want to see what's happening to x. So basically undistribute the 4. And so when you do that, add parentheses and then divide this c value by whatever this number is. And so when I do that division, that creates x plus 1. And then if you were to graph both of these in a calculator, just looking at the equation, you would think it's left 4, but you're going to see it only moves left 1. And so that's why it's very important that you have it in the proper form. Otherwise, you're going to misread what's happening. And so your first step, always, throughout the entire year, is to make sure if you have a scale factor inside the function, inside the bars, you need to factor it out. Add a parenthesis and divide. Okay, and so now that we've done that, we can identify our transformations. We have a vertical compression by 1/2. We have a horizontal compression by 1/4. We have left 1, and that's the most common mistake I see throughout the year, and then a down 2. It's not factoring out the 4. Okay, so to graph this, our vertex left 1 is going to put us at -1, down 2 is going to put us at -2. So -1, -2, there's our new vertex. There's no reflections, and so we know it's still opening up. And so my range is going from -2 to infinity. Axis of symmetry, steal the x coordinate at -1. Don't forget your x equals. Domain, all real numbers all the time. Okay, to get our slope, we take our a times our b. So slope is 1/2 times 4, which is 2. So that vertical compression makes it wider, while the horizontal compression makes it narrower. So that's why this 1/2 kind of cancels out the 4 just a little bit, not all the way. And so our new slope is 2, so it's still going to be narrower than the parent, who has a slope of 1. And so we go up 2 over 1, up 2 over 1 on each side. I like to fill the graph with as many points as possible to get a really accurate graph. And then if you're using pencil and paper and want to use your ID or credit card as a straight edge, that's what I do. Oh, I messed up that point. All right, so the last part of these notes is they are going to give us the transformations and we're going to give them the equation. Okay, and so each time we're going to have absolute value bars. And so we just have to decide where the scale factors go, where the numbers go. So this first one says reflect across the x-axis. That means I need a negative outside the bars. And then down 1, that means I need a -1 at the very end outside the bars. And so my final equation, written a little bit more concise, is negative absolute value -1. Okay, this next one says reflect across the y-axis. That means my negative is inside the bars on the x. And then down 8, that means my -8 is outside the bars. Okay, next up, I have a vertical stretch by 4. And so here's my bars. And my vertical stretch by 4 would be outside the bars. And then left 3 means I have +3 inside the bars. Remember, everything inside the bars is opposite of what you would expect. And then down 2, we would have a minus 2 outside the bars. Since it says equation, make sure you have a y equals or f of x equals. Okay, next up, horizontally stretch by a factor of 3. So that means my scale factor is inside the bars and it's opposite of what I would think. And so that means there's a 1/3 inside the bars. And then it also says shift right 5. So remember, proper form, you have to have an extra set of parentheses so that scale factor isn't sitting right next to the x. And then we can put the plus 5. I mean minus 5, because it's right 5. Right 5. If you just write 1/3 x minus 5, that you can graph it in a calculator. It will not move you right 5. It will move you right 5/3 or 15 or yeah, 15. And so add your parentheses so that it moves right 5. It has to be minus 5 from x and x alone, not 1/3 x. Okay, and then lastly, the up one is outside the bars. Next, we have a reflection across the x-axis. So negative outside, horizontally compressed by a factor of 0.5, which is the same as 1/2. And so that means, since it's horizontal, it's inside and it's opposite. So take the reciprocal and put that factor inside. Since that's all that's happening, we don't need the parentheses. It's only when you have a scale factor and a left or right translation. Okay, next, horizontally compress by 1/3. That means I'm going to have a 3 inside and then left 2. Add your parentheses, then put your plus 2. Close the bars. And then up 5. Put your y equals. Right, this next one says our vertex is at 1, 3. Remember, the starting vertex is 0, 0, so that means we have moved right 1 to get to the 1 spot on the x, and we have moved up 3. Right 1, up 3, and vertically stretched by 2. And so the 2 goes outside. Right 1 is minus 1 inside, and then up 3 is a plus 3 outside. Put your y equals, and we're done. Okay, next vertex is 0, 4. That means we did not move left or right, but we did move up 4. And then it says our range is negative infinity to 4. So that means that 4 is our maximum. That means it's upside down. So that means we had a reflection across the x-axis. And so when I'm writing my equation, I have a negative outside the bars. And then the only other transformation was up 4. So plus 4 outside the bars.